clear to me that everyone really knows what EarthCARE is all about, and so the science behind it. So I'll go through this. So some of the stuff will be outdated. I think this presentation, in spite of the fact that it's dated 1st of October 2024. I know I probably, that's something PowerPoint is just done, because I don't think that may be the last time I opened it, but I know I made this presentation back in 2017 or 2018.
Oh, okay.
So,
Retro style.
So let's see if how my memory is. So one of the good sources for learning about EarthCARE and the science and the goals and even the instruments and a broad overview, of course, is a BAMS article that is now nearing a decade old, but it's still there, and it's still a useful reference if you want to get up to speed. And because especially the high-level science goals haven't changed. Of course, some of the instrument specifications and performances have changed, but the basics remain about the same. If you go to the BAMS article, it won't look like that, because that's a very special one. Of course, that's where all the current members of the mission advisory, the joint European, Canadian, Japanese mission advisory group, you have all the signatures there.
Only the advisors of the people who were doing the work.
Yes, at the time, and that was all signed at a meeting in Tokyo. And sadly, there's a couple of there's one signature that's of someone that's no longer with us. We had the program manager die unexpectedly about a year ago. It's Tobias Unitobius. So we've not only, and there's a couple of going back more in history, a couple of people that are no longer with us. So the satellite business these days, you can, for any major program, you can count on a long trajectory. And if you're lucky, it can, and if you let that kind of thing continuity, like I do, you can sort of get wrapped up with it, and then your career is kind of, your career trajectory is straight. You've got a goal, but then one day you look back and say, "Oh my God, it's been 25 years." Now it's up. But I have done other things. So I stayed at KNMI, of course, but I've stayed there, but the place has changed so much it feels like I've had several jobs. So that's okay too. But some people get bored if they're going on more than 4 or 5 years at the same place, but that hasn't. So EarthCARE is and still remains focused on shedding some more light between this nasty triangle here. It's the coupling between clouds, radiation, and aerosols and dynamics in the atmosphere. And where it begins and where it ends is hard to say because it is a cycle. So clouds are very diagnostic of the state of the atmosphere. If you have a cloud, it means there's a certain temperature and relative humidity there in probably aerosol environment. And clouds obviously affect the structure of the atmosphere. They reflect solar radiation and trap thermal radiation. And that affects the heating rate of the atmosphere, which changes the circulation. And then introduces, the clouds help drive the winds help and define where the clouds are, etc. So that's why it remains let's say, an essential area, after decades of hard work, still remains a challenging area when it comes to both weather meteorological models, so short-term weather prediction, and arguably the more important aspects of long-range climate forecasts. It still remains, pinning this down, remains, let's say, one of the largest sources of legitimate sources of uncertainty in our ability to predict future climate. And the more we learn about it, the more we learn about it, we think it's a tractable problem, but still, it's going to take better observations are certainly and better modeling are certainly part of the solution. So in EarthCARE has 4 instruments, and its idea not only we focused on this. Let's say you can think of this triangle as a bit of synergy, everything interacting. EarthCARE itself is sort of like its own interacting system. So we have 4 instruments, a advanced cloud aerosol LiDAR, so it's a high spectral resolution LiDAR. So I'll explain what that means in another couple of slides. So it is an advancement over backscatter LiDARs like Calypso. We won't reach the lifetime of Calypso, which should be in a...
Because it is an HSRL. It is a...
We're a little lower orbit. The laser, it looks like the lasers would last as long, but it's, well, I'll talk about that later.
Okay, yeah, next topic.
That's there. There's also a cloud profiling Doppler radar, like CloudSat, but it has a Doppler capability, so we can measure fall speeds. And it is a little bit somewhat more sensitive than CloudSat. There's also a multispectral cloud aerosol imager, so you have the 2D, so the LiDAR and radar give you the horizontal context, the vertical context rather, and the multispectral imager gives you the 2D view like that. And there's strategies to put them both together. And on top of all this, you have a 3-view broadband radiometer. And that gives you the, oops. Okay, I'm explaining things too.
Can we ask during the presentation?
Sure,
or
go ahead.
maybe wait?
Yeah.
So I want to ask you about the multispectral imager. What would be like the footprint or the
130 kilometers, 500 meter resolution, with, I can't remember the wavelengths of the bands off the top of my head, but they're kind of what you'd expect from it. There's a slide, I think, around that.
Okay.
And to top this all off, you have a broadband radiometer that's measuring both the total reflectance from the Earth to get the total shortwave albedo, and then you have a long wave channel, and you have the 3 views because you can't really measure a flux from space, but you get a much better idea if you measure the radiance at 3 different angles. And the idea is to put this all together, and it's kind of like and then that gives you the ability to do kind of an online closure experiment. So the LiDAR and radar give you the best vertical profiles of, let's say, the cloud and aerosol properties along the nadar. With the help of the multispectral imager, you can expand those retrievals out to a certain footprint on the order of 10-20 kilometers. Then you can do radiative transfer on that retrieved structure. And then you can actually calculate what, let's say, the broadband radiometer should be seeing. And if they match, that means your retrievals are self-consistent and you probably understand what's going on in that section of atmosphere. If they don't match, well, it could be something wrong. It could be a trivial software bug in the system. But if you, let's say, after we have enough measurements of different conditions, the actual science will be tracking down the circumstances in which we cannot get radiative closure. So if the retrievals are saying one thing and then our broadband radiometer says, no, you're missing something here, then that points to fundamental things such as we're not using, let's say, the right isocrystal models in scattering. The properties we're assigning to the aerosols aren't right radiatively. The surface temperatures are off, or etc. So that's one thing. So at the end, when everything gets up and running, we should be able to deliver to the scientific community products that are at least have this self-consistency check, which is a step above what most satellite missions can do. So even if we did not have collaborative measurements, which by the way are extremely valuable, we still could do the consistency check. And I can, so I covered most of that already. Do I need to review the idea of radiative balance in the atmosphere? Probably.
No.
No, that's fine.
Okay. Cloud feedback question, we went all through that. That hasn't changed too much in the last decade. Blah, blah, blah.
That's the question.
Sure.
Very simple in comparison to your project. Do all those data, is there a way of collaborating with agriculture, fishermen? I mean, this is how with my simple mind, like when the fishermen in the past or people who were, cultivate, the agriculture, they could see, those changes in the atmosphere and I'm sure, of course, it's not from a scientific point of view, but and again, I do apologize if it's a very, I'm new to the field, but is this, does this science also support agriculture?
Indirectly, I mean, you do have satellite measurements that are specifically, let's say, for crop health assessment. This isn't one of them, but this data does help both directly and indirectly producing better weather forecasts.
Fantastic.
And that, of course, is interesting for everyone, especially for farmers, for example.
Yes.
So that's one segment of society that benefits directly from even small improvements in weather forecasting.
I think
And I mentioned, and we'll get to the uses of the data because EarthCARE does have an increasing role in providing data that will be directly used for weather forecasting. That wasn't within the original mission mandate, but it's becoming quite exciting. So that's the geometry of the mission. So like I said, you have the LiDAR and radar pointing down. The CPR, the Cloud Profiling Radar, is an instrument provided by JAXA, so that's not a European instrument. It's provided by the Japanese Space Agency, and it's actually built, though, by another Japanese agency, their National Institute of Communication Technology. And it's pointing straight down. And well, I'm giving nothing away, but there was post-launch, there was a lot of concern about how good the pointing is. That especially for the radar, if it's off a bit, that really screws up the Doppler. But it looks like we're hitting the ground within much order of a beam width. So in the order of like, if we predict the beam center's down there, we're like 20 meters off. So it's really solid. And after too, the pointing is spot on. The ironic thing is, so for the CPR, the Japanese had, until they refined it, had a model for where the antenna, which is quite big, should be pointing because of thermoelastic deformations along the orbit. But the model was actually amplifying everything.
Oh.
So at first it looked like the thing was swinging wildly, but when we turned the model off, so the knowledge of the pointing was bad, and when we assessed what the real pointing was, it was right on. So they do a better job just switching the model off. Don't spread that story yet; it'll become common knowledge soon, but still.
So they have put much more errors there.
Yeah. So this is one instance in which, let's say, the correction procedure was.
Overcorrected.
Yes.
And CPR is the first radar there in space that measures updrafts and downdrafts.
Yeah.
Doppler. So this has never happened in the past. There are several other radars in space, but this is the first that will be able to measure vertically the updrafts and downdrafts.
Yeah.
Can I ask that the temperature and the pressure
The profiles, where do you take it?
That comes from the ECMWF
Okay.
forecast.
Okay.
Yeah. So, and that data is integrated in the data processing and available to all the end users too. So, that's that is important.
They are provided with these auxiliary files, right?
Yes, and some of
You know, the-
it's we have the XMET product, which is but also the level 1 LiDAR, the ANOM, has the temperature and pressure profiles in there too that were used to process the data.
Oh, they're integrated already in the files.
Yes, because they were necessary for they were necessary to it's necessary even at level 1 to ingest that data because the line profile in the Rayleigh channel of the Rayleigh scattering depends on the temperature and pressure, and that has knock-on effects. So that'd be really convenient. So to have it there. So do I need to explain what a LiDAR is? That's
That's great.
no.
Oh, you were
But it's
prepared
nice
for that.
animation.
Nice. It's a very nice animation.
Yeah. So of course we had to compare EarthCARE with the A-frame, the combination of CloudSat and Calypso. So they were both launched in 2006 and were groundbreaking and lasted a whole lot longer than anyone would have guessed.
Oh, they were waiting for EarthCARE.
Yes, we didn't quite. We will have a gap, unfortunately, but and there will be a lot of blood, sweat, and tears spent in trying to bridge the gap between the two instruments, both CloudSat and the CPR and Atlas and Calypso, which are essential, but there's always going to be uncertainty. It would have been better if we had direct overlap. But. Just to remind everyone why it's a good idea to combine LiDARs and radars, especially for cloud measurements, is that it's what the instrument sees is it's all relative to the size of the wavelength you're using and the size of the scatterers. So for a radar, you see something like the square mass distribution. And a mass is proportional to the diameter, the cube of the diameter, that's where you get the reflectivity, and that leads to the reflectivity being the proportional to the 6th power of the diameter of the droplets. So that means you see big particles, precipitation droplets, and ice crystals in the atmosphere with the radar. Very good for that. Anything small like an aerosol or even non-drizzling stratocumulus, not so good. The LiDAR, on the other hand, sees something like the area, so d squared. So that means you're very good at aerosols, molecules in the atmosphere itself. And because the interaction is so strong, though, attenuation is a big thing.
Also, the super cool layers, they are so small, but they're not detectable from the radar.
Yeah.
There you use the layer.
So that's why it's essential to put these together. And this is an example with CloudSat and Calypso, where you see that they're all looking at the same bit of atmosphere, but if you look at the CloudSat image, you notice you penetrate much deeper into the clouds. But you miss a lot of the thinner structure above, and the LiDAR is picking that out quite well. So by putting both of them together, you get a much better picture of where the clouds are and their properties. And in the area where you have overlap, you can do things like retrieve the particle size. And there's even more advanced methods that bring into things like the brightness, temperature, and reflectivity above to fill in a lot of details in the vertical profile that you would not otherwise be able to handle. And this is all explained in a lot of detail in one of the papers of the EarthCARE special issue, which I'll talk about later. And I'll just now Now we'll just focus a little bit on APLID and then probably wrap up this part. So I mentioned that APLID is a high spectral resolution LiDAR. So what does that mean exactly, and what advantages does that give you? Well, a high spectral resolution LiDAR, in that case, unlike a normal backscatter LiDAR, you're looking at very small spectral bandwidths, and the advantage of that is that you can begin to tell what you have scattered off of. The problem with a backscatter LiDAR is, of course, you only have one signal, really. And you do not know, per se, if that's photon that you're receiving, if that's scattered off the background atmosphere, if that's scattered off an aerosol or a cloud particle. And if you see an attenuation in the signal, your signal, let's say, starts at a baseline and then goes up and then fades away, you don't know if that fading away is due to the fact that there's less cloud or aerosol there, or your signal is being attenuated. And you can do retrieval methods like the PLET method, but then you have to assume what the extinction to backscatter ratio is. With an HSR LiDAR, you can do something different. Like in a Raman LiDAR, with an HSR LiDAR, you can, if your instrument passband is like this, and this is your laser frequency, the spectrum from the atmosphere looks sort of like this. So this broad feature there, that's the scattering from the molecules themselves. The neural peak is from the laser itself. And you split this in a filter, so one channel gets more of the particulate scattering and less of the molecular scattering, and the other channel the opposite. That enables you to decompose the signal into components that are scattered from the molecules themselves or the particles. And the advantage of doing that is that if let's say your air density profile looks like this and you're looking like above, in the me channel, or this is the particulate channel, you will see nothing until you hit the cloud, and then you see something. In the Rayleigh channel, it'll follow the molecular atmosphere above, and then when you enter the scattering layer, you don't see any enhancement of the signal. You only see the signal fall off, so you get a direct measure of the attenuation. And that enables you to separately measure the backscatter and the extinction. And you divide the two, you get the extinction to backscatter ratio. And for aerosols, why that's a big thing is that nature cooperates to a certain degree. If you're interested in what these aerosols are, then you are able to take two measurements. Instead of assuming the LiDAR ratio, you can now derive it. And you can also measure the depolarization ratio. I forgot to mention that APLID is polarization sensitive, unlike AOLIS. And then this allows you to a certain degree, classify what these aerosols are. Now, for people that are interested in doing the simulation of the data for aerosol purposes, you would not necessarily need this knowledge, need this classification, because you probably should be then assimilating the level 1 signals themselves. However, you should also have in your simulation system the freedom to assign the LiDAR ratio depending on the microphysical properties of the aerosols that you have. So, but we're still, so we you may not be using the aerosol piping because that's crude, but you should be predicting what the LiDAR ratio is to do in the simulation system. So, but then you really have then two almost independent pieces of information that should help, that would help really improve the sources, depending on the speciation.
So now ECMWF, that they have already worked in advance to assimilate the APLID product, they will, in the future, they are planning to enhance these assimilations with assimilating also the LiDAR ratio to improve, as Dave mentioned. we will be working on that from now to give them the correct parameters for that.
And of course, it's a growing area of importance. Well, I don't have to tell you about direct effects of aerosols around here. You're often subject to quite big plumes of Saharan dust, which I'm sure are affecting the short-term weather and the longer-term climate.
And in your question, they have told us that the years that there is more dust, there's more honey production from the
Really?
bees. Yeah, and also the dust affects how much fishes are in the sea because they eat more from the iron and then
That could be, yes. I mean, the desert dust transported across the Atlantic, I've been told before, that plays a big role in the Caribbean ecosystems, because it's actually one of the major inputs of iron into the environment there. And that's several thousand kilometers away. So.
And I have also seen, because of the dust transport, increase of the phytoplankton on the sea surface. So increasing the food for fish, so more phytoplankton, more food, more fish.
Yeah.
And actually, I think it from a very simple, an outsider, this is amazing that this science is so much involved, because unfortunately or unfortunately, the new generation has moved away from agriculture and from our, I'm talking from Greece point of view and villages, and they haven't learned from their ancestors how to cultivate, to understand the weather, the clouds. And so even if they wanted to go back to the village, go outside, back to, the rural way of living, they wouldn't know how to assess the information and the data to be able to continue the cultivation of whatever they have, the olives, honey, for example. So this marriage of this project, research, mission, and data with the new generation knowing how to read this data to apply to their land or to the sea, to fish, this is how I see it, from an amazing way of weighing those two.
In this way that you're thinking, there is the Copernicus mission.
Yes.
They have actually next week, the 11th.
So that's an exciting time. I'm quite removed from that area, but no, the bridging the gap between, let's say, the scientific products and products specifically for agriculture or urban planning or even health.
Yes.
Or public health is an area that is.
So the Copernicus missions, all the sentinels that Athena is working also, they all, because they're geostationary or they are reoccurring every day, they are products tailored for specifically with the idea for what you mentioned. And also the fact that ECWF is assimilating a lot of this product. This mission now is more about science, because it is on the science part, where it is about finding unknowns, which then they can help, for example, in better parameterizations in the Sentinel products, in order to have better products there.
And essentially match and bringing the gaps to,
The knowledge gap.
Our mission lifetime is rather short
3 years.
for that time.
Yeah.
It could be longer.
Yeah.
There's now serious
3
discussion.
plus.
Yeah, but there's now serious discussion now about if things go well. People are talking somewhere on the neighborhood of 10 years.
Oh, really?
It's still very preliminary.
You think it could last so long? Because
If there's a whole strings of ifs, and it would involve moving the orbit up, and the analysis hasn't been done yet.
okay.
But ESA is willing to look into it.
This is very important, because now that the NASA has cancelled the AOS mission, it is a big problem after.
Yeah, but Caligula it's coming, but I don't follow.
But in a lot
Yeah,
of years,
but
this is still a
there's
concept.
still a lot of ifs associated with Caligula.
And there is still a concept. This is still a concept mission. That means maybe 23 years.
The only thing I'm certain about Caligula is that they're going to change the acronym.
That's a good choice. It's a good thing to say.
As NASA's getting much more, is always very PR
Political.
conscious,
Yeah, of course.
and Caligula is the mad Roman Empire emperor is not so good. And more importantly, Oh, this is a little bit off color, but I'll say it anyway. In the 1970s, Penthouse, you know, the porn magazine, that's made a full-length feature film starring even like Peter O'Toole and a lot of gay-class actors, but it was an X-rated film. It's quite notorious. So if you mention to an American colleague, I don't know, a certain age, they think of the Penthouse film and all the gorgeous.
We are
And they're
recording.
re-releasing that. A remastered copy.
I see, I see.
Like in the theaters.
I see, I see.
So,
Okay.
so Caligula, I'm sure if it proceeds with NASA, they will be changing the acronym.
I see, I see. Dave, keep in mind that your presentations, we record them for the
Oh,
website.
further.
We can keep this for the coffee break after.
Okay, very good. Anyway,
Can you explain its lifetime of EarthCARE?
Yeah.
What is the expected lifetime of EarthCARE without this idea of extending?
it's,
3
of
years.
course, it's 3 years plus since the mission, the stated mission goals. But my personal opinion, not speaking for ESA or whatnot, but my expert judgment based on all the rumors and facts that I've heard is on the neighborhood of 5 years.
Okay, interesting.
But it heavily depends on how well they learn to maneuver the platform, how much fuel they need to maintain the orbit, and solar activities. Still a lot of things.
But also we have to hear with the Galval.
Yes. So I'm not the best person to handle
Up to the point.
any questions about the CPR? I guess you had Pavlos and Alessandro here earlier.
Yes.
So I'll skip that. CPR, great instrument.
It has provided data already.
Yes.
All the instruments, they have provided data already, which is very short for a mission.
Yeah. And you had some questions about the MSI.
Yeah.
So if you can read that.
That's your resolution.
Yeah.
Okay.
So it's a rather small instrument. It's not like MODIS.
Mhm.
It's not as capable, but you still can do quite a lot with it.
Sorry, I'm not used to the word swap. Is that?
Well, that's
An observation?
the long track,
Okay.
not the cross track.
Okay.
So the nadar is here and the swath is the horizontal.
Okay.
Extension.
Do you think with the responsibility to do a kind of SIP track climatology out of this, like to track the SIP emission? Using like there is a kind of approach from MODIS, basically.
Yeah, yeah.
Also use like machine learning techniques to make like.
Yeah, I'm sure they can be done in the, we don't have the swath of MODIS, of course.
Mhm.
And you will, and you won't, the LiDAR won't hit the ship track as often as the nadar, but a few months of data, I'm sure you could get something.
But maybe with MSI it has bigger track.
No, it's only 150. Well, it's actually 130 kilometers is more accurate. And then you have the broadband radiometer, which I won't say too much about. But it's also quite a nice instrument, and it's actually it does deliver product. It does deliver images too at the 10 kilometer scale. So you'd actually get images of the fluxes at the top of the atmosphere.
And the point
And
here,
there's some we don't have too many products that use that directly, but I'm sure they will be coming. So that could be something that's the use of this high resolution total wave measurements, I'm sure will be enhanced in the future. No, it's 1 by 1 kilometer or something. Yeah. So you have. So the images that have already been released look quite nice. And this, I won't say too much about it, but EarthCARE has
simplified.
this is the simplified data processing chain. There's something like 47 products in about 30 or 20 some processors, all organized into different chains. Of course, we have the level 1, and then we have the level 2A. So we have a number of single 2 products, and then the level 2B, which combine either multiple single instrument products, both in the level 1 and level 2. But if you simplify that even further, this gets back to the sort of the idea that I talked about earlier of the online closure, in which you have all of the you have each instrument first doing its own retrievals of what they can without cooperation with the other instruments. Then at the level 2B, you get the fusion of the different instruments to give you, and that's synthesized into these scene reconstructions in which you have an estimate of the 3D properties of the atmosphere. Then we're applying actually both a combination of 1 and even 3D radiative transfer calculations. It takes a lot of CPU calculations, but we're doing that. And then we have the online closure assessment. And it's early days now, and not all the products have been validated by any means. But at least on the technical level, the code has all been demonstrated that it's running in the operational processors. So this assessment, even now in the commissioning phase, is happening. There's many bugs. We're not within our goals yet, but it fundamentally looks like it's going to work. Of course, there's hundreds of bugs and things we still have to track down, but even not too many years ago, there was a lot of skepticism that we would ever get this running. And it's only because we had literally decades to prepare for this that we were able to do a lot of no, I don't have. That we were able to do a lot of simulations, and we had developed through the years a number of scenes, but the ones we developed officially for the algorithm development and ground segment testing were based on high resolution cloud resolving forecast models. And one of our scenes is a so-called Halifax scene. So there's a number of high resolution cloud modeling scenes all stitched together in an orbit that goes over Halifax in the province of Nova Scotia in Canada. So within a couple of 100 kilometers from my hometown.
And then you're from Canada, right?
Yes,
You're Canadian.
Yeah. From about right there. So these scenes were used as a basis, and on top of this, we had aerosol fields from the MAC project to be able to transfer things like this is the model extinction along the nadir track of that scene, extracted from there, and from that to use this as a basis for modeling, in this case, what Athlid would see. And this is starting over Greenland, and you can see the LiDAR is picking up these ice clouds here. It's missing this very weak feature there. It's also important to know what you see, but also what you won't see, what you could be missing. A lot of super cold water here. You're hitting a storm above the near Nova Scotia, and you can just see you're seeing the cloud tops here, more super cold water there. And out here in the Caribbean, you're seeing two aerosol layers. So down here, it's mainly marine sea salt mixed in with some cumulus clouds. And above here, you have some more continental pollution coming off the eastern seaboard of the US. And we can then apply our retrieval algorithms, which I'll talk about in detail in the next, I think it's the next presentation, to retrieve things like the LiDAR ratio. Instead of having to assume it, we can retrieve it. And in this case here, you see a clear contrast between the sea salt below and the so-called continental pollution above. And this is what the truth would be. You can see it's not, we can't follow things perfectly, of course. But one of the challenges is to you only have a limited sensitivity, and the signal to noise ratio of any space-based LiDAR is always going to be less than a ground-based one, because you're at least 400 centimeters away, and the receiver of outlet is only a telescope like that. So, but it's impressive what it gets. And at the end of the day, we can, in terms of the classification, we can do what we considered to be a fair job of separating different aerosol types, but also separating the ice and liquid phases. And of course, this is just the beginning of the chain, because this is then combined with the multispectral imager information and the cloud information and the radar information to get really even more sophisticated and better classifications and better cloud and aerosol properties. So the data usage, there'll be a lot of this data will be used in evaluation of parameterizations and process studies coupled with models to see if the models can actually replicate what is being seen by the actual observations. There is this crucial one here, and this has only increased in strength in the last few years, is that a lot of the products will be operationally simulated on a trial basis by the ECMWF. Not only the cloud profiles, but also from the aerosol side of things too. We're hoping for, and already some of the preliminary results are quite encouraging.
True.
And it's nice too with the ECMWF with the weather centers that are simulating the products also are able to give a feedback into things like the accuracy of the calibration. Because if they first have to monitor the quality of the data before they know it's a certain quality, before they can use it in their models. And in this procedure, they're very good at detecting when there's, let's say, step jumps where something is wrong in the data. If the calibration, the sensitivity of a component changes, that will be that.
Relationship.
Yes.
Relationship.
So that's another important part of the quality monitoring.
And they do it globally, so
Yes.
very interesting.
And I'll wrap up there. So I hope people felt that was a little bit worthwhile for some of this people. I'm sure some of the audience, this was nothing new, but for others, I think it might help set the stage before I go into some of the details of LiDAR multiple scattering, for example.
Very nice overview. Thank you very much. Questions? Let's open the floor for questions.
I have two questions. One is more technical, like on the products. Do you think there would be like a way to have a product like cloud optical thickness? Because from CloudSat and Calypso, this is not, there was some effort with this Tau product, but I think, especially for me, it's interesting because within the Obsidian A band, we are able to retrieve the optical thickness of the cloud, and for me, it's like a challenge to combine it with active remote sensing and.
Yeah.
Okay.
Okay. So let me.
I cannot.
You can't see it here, but let's see if I can find it.
Whatever is yellow is a CPR product.
Yeah. This is.
Purple is Athlete product. This is the BPR product, and the green are the MSI product, and then the gray are combinations.
Yeah. So, but there is if you're familiar, people have recognized that, we have recognized as the algorithm developers that there's a large heritage from CloudSat and Calypso, for example. So we have I think maybe it came later, but there should be an A-lay product here, and that is a layer product. So this is being developed at Tropos in Leipzig. It was Ulla Vonnegut pressed for that, and that's a product in which they bin things by layers and types, and one of these is the cloud top, and there's another one of cloud layers, and they report the optical depth of these layers.
Of each layer.
Yeah. So it may not be exactly what you're used to, but if you're familiar with what was done for Calypso, for example, it'll be much closer in that regime. I mean, but let's say for the real experts, they can also use our combined target classification and the extinction field and go and do their own bidding. But we're trying to make this easy for people. So the short answer is yes, but things are never exactly as the end users want because you can't please everyone. But we are trying to make the data in that respect user friendly.
My second question is with respect to synergies with other satellites. Do you plan to show us some more slides or?
Yeah, well, not so much because our opportunity for direct synergy is somewhat limited. Because first of all, we're in low orbit. We're in ascending node, not a descending mode. So that means we're
Three, for instance, like will you have any like?
Yeah, we do have some regular co-locations with what platform is PACE on?
PACE, okay.
Yes.
PACE, so another.
Yes. But we cross a few times predictably, but we're good. Yeah, they're going up and we're going down, or vice versa. So we get a lot of cases like this. But and there's actually through in the AirSense project, there's actually some preliminary comparisons in the right conditions. You know, when it doesn't work so well for clouds, but in extended aerosol fields, we're getting reasonable comparisons already. And that's a completely different, and this is the LiDAR versus a polarimetric scanning telemeter. So two very different ways of getting the aerosol optical depth, and to my opinion, much better than they have any right to be at this stage before everything has been validated.
In the Aerosol project, it's an ESA project, an ESA project.
Which one?
The AirSense.
AirSense. I know, yeah.
With all of them.
Yeah, and this is tied in, and a lot of the same people involved in these efforts are also involved in certainty in the clean clouds.
Yeah.
So it's we're looking forward to a lot of things.
And more synergies in the future, because in the future you will have Sentinel-4.
Yes.
With geostationary, and then.
Yeah, and of course, I forgot to mention of course, you can always co-locate with the geosynchronous satellites. And there are people, I'm sure there's people that have plans to do that. I don't personally have, but
Yeah, because you have to concentrate on fixing.
I still have to get the
data every week.
I still have to satisfy the people at the level 1 stage first before. But eventually, when everything gets solid, I want to actually go back to what I got into the business to do in the first place, and to say something about what's going on out there. So in the past quite a while now, I've been doing a combination of let's say instrument engineering and software engineering, but eventually I want to go.
With science.
Yes.
Thinking that
Not that what I consider I'm doing is unscientific, but it's maybe a little bit too much engineering
to work more of the data to see the physical information there.
Yeah.
And then we have also one more question from Nikos on the chat.
So,
Nikos, would you like to ask your question?
I think it was answered during the talk afterwards. You know, I mean, if EarthCARE will overlap with another.
Can we hear him?
Can you hear me? No, you
he's
can't.
put something in the chat.
Yes, and but hoping he can ask his question.
Okay, let's do something else.
We cannot hear you. Can you talk again? Φαίνεται να μιλάμε.
No, we're speaking.
No?
Can you hear me now?
Yes.
Okay, I mean, I'm struggling with my speakers. Okay, I think this question that I made that I made is has been answered during the talk. I mean, if the question is if EarthCARE will overlap with another one.
But for the end, you asked for the end of the mission, and this we haven't discussed. Yes,
Okay.
if there is a foreseen something for the end of EarthCARE and an overlap with another satellite.
You mean like adjusting the orbit to better match something? It's
No,
No.
I guess to have an overlap with another future LiDAR mission.
Yes,
Nikos.
exactly. I mean,
Oh,
that
we're
was
using
just
an
a
overlap
curiosity.
time. Well, that's a good question. Tricky. Given the state at which things go, I would not expect a.
Aeolus 2, for example.
Aeolus 2 is probably the best bet. If there is going to be an EarthCARE 2, they would have had to start at 5 years ago. But who knows? It's continuity is a big, it's a big question mark these days. Like Eleni mentioned, there might be some overlap with Aeolus 2, which will, and that mission will still be primarily for winds, but it will be much more capable for aerosols than Aeolus 1, for example.
Mhm.
It won't have the LiDAR radar synergy aspect.
They approved the channel, they approved the Aerosol channel, right? The depolarization.
Nothing has been signed off on yet, but it looks very promising for that.
Do you remember when is the time that now they expected for the first launch?
Yeah, I dare not to say, but it won't be before probably 2030.
So this is only if we elevate EarthCARE to
Yes,
higher level.
that's one of the reasons we want to do it both not only scientifically, but with a somewhat higher orbit. There might be, there was some speculation that maybe then some of the other agencies might want to launch some microsatellites to orbit with EarthCARE.
LiDARs, microsatellites, or LiDARs or something else.
Having a microsatellite carrying a LiDAR would still be it's still,
Big
that's
psychologically
ambitious.
What CubeSats? What the
CubeSats, but still, yeah, with a LiDAR, a lot can be miniaturized, but the need to have a reasonably sized telescope and a powerful laser to collect enough photons, it's hard to get around the physics of that.
So the mini satellite.
A mini nuclear reactor, maybe, but then that doesn't really exist.
I have a couple of silly ones, questions. I mean, if you want, I can ask.
We want, Nikos. Yes, you
Okay. Okay. I wanted to ask you about. I know there is a paper outside on the topic. Is the aerosol typing? No, that do only two kind of intensive properties can give us this detailed aerosol classification. I mean, is it enough?
Let's go back to. Let's see if I can find. Short answer. What do you mean by enough? The question.
I mean, okay. I mean, more specifically, we don't have the information. We don't have spectral information. For instance, thinking of like a color ratio or a angstrom exponent that would give us, a size. Let's say information regarding the aerosols up there. For instance, just.
Yeah. No. Yeah, we have a particular need now. Okay, you do have a good point. We have measured the aerosols and at one wavelength here at 355. And then in some circumstances, we have the optical depth estimates from the multispectral imager.
Mm-hmm.
So we'll have some idea of the angstrom coefficients.
Okay.
But we needed to go to some sort of typing too for not only the fact that people are interested in general in the typing, but we need this typing to connect it with aerosol models that enable us to extrapolate the extinctions and single scattering albedos out to do the broadband radiation calculations. And for that, we are wedded to this PTAC approach of Ulawanner, of which there's a paper. But if you ask me, no, if we wanted to, and this will get us so far, but it's not perfect. Even with this typing here in reality, when you start filling this in with more observations, you get a lot of, there's a lot of overlap. Even, even in a simplified diagram, the ellipsis, for the ellipse with smoke, largely overlaps with the pollution.
Pollution, yeah.
Pollution. So it would be nice, speaking of as a LiDAR person, it would be nice to, let's say, have the backscatter extinction at 532, for example.
I mean, and something else. I mean, on that, technologically speaking, I mean, is it possible to have a dual wavelength high spectral up there?
Yes, I think it's completely feasible. It's just a matter of cost and resources. I'm hoping that people's that we'll see a reinvigoration of such ideas and such aspirations once EarthCARE has proved itself in orbit, and I think it will, because it looks like, of course, anything can happen tomorrow. But till now, the laser has been very stable. The crosstalk has been very controllable. Unlike Aeolus, the laser appears to be very stable in frequency and is behaving very nice. And there was a lot of people that were doubting that would be the case. So yeah, I think now that there's been a lot of teething pains with the development of lasers in space, but I think we've hopefully we demonstrated that if you do it right, you can do quite a lot. But it's a matter of cost and resources and
of course.
community.
And I have a last one, and I will not bother you anymore. I would like to ask something regarding the color scale that has been chosen, to showcase, the maps of EarthCARE. I mean, I've seen that it looks like, something like the color scale used by Calypso. But my question is a bit provoking. I mean, considering the fact that these blue to red color scales usually, they tend they are not good enough, meaning that they are, used in meteorology, for instance, to showcase anomalies, like going to cold to, from negative values to positive values. Having a color scale that uses blue to red somehow is not inclusive. I mean, and my question is this now: if this has been thought, to change or using like a more inclusive color map, color scale, not color map. No. Okay.
No, well, it depends. I mean, it's color scales are something a lot of people are increasingly paying importance to. If you publish in AMTD, for example, they encourage you and they force you now to make sure that your color scales are colorblind friendly. Exactly. So what I'm showing on the screen here now was something produced in 2017. Before we were really thinking of that. So if you go to the EarthCARE special issue, you can see that at least some of the authors now have moved their color scales in that direction.
Okay.
Be sort of colorblind friendly. And I know there's some people thinking about it, like Dave Winker, Mr. Calypso, at the last ILRC, had a poster dedicated to nothing more than the choice of color scales for plotting LiDAR data, for example. So it is something that's being taken more and more seriously.
Okay, perfect.
Nico and Calypso team, now after that the Calypso has stopped measuring, they are working on and they are processing for the version 5. One of the points they are working is a better color scale for specifically to be more inclusive for also colorblind people and to get over this fake artifact that you mentioned. And I have seen some presentations about this. This is a presentation. They haven't mastered it to know for sure that this is it and we go with this. But we are observing. So in the tools that they are developed in ESA, the idea is to have more than one color scale. So we have asked to have the Calypso color scale. Maybe we can ask, this tool hasn't been finalized yet. Maybe we can ask also to have this version, the colorblind version. And if you have another suggestion of color scale, you can write it in the chat, or you can even write it in the forum.
I think they are stock one. I mean, all the programming languages, they come with, you know, like libraries of, let's say, color scales anyway. So,
But
no, just a curiosity. It was just simply a curiosity for me, you know, from my side.
But the important thing is that because the people who are developing the programs for the operational products, they are not LiDAR experts. So it's not, for example, you, me, or Sharon Mason, or Dave who will do this codes for the automatic product. They don't have this detailed expertise. So that was the case with Aeolus, that they came with a predefined, very bad color scale that was didn't highlight that actually it was visible only the clouds in the color scale that was officially provided with for Aeolus. You couldn't see the aerosols because you need 3 orders of magnitudes to be able to separate in one order of magnitude the clouds, in another the dense aerosols, and another the fine aerosol layers. And this, they didn't have these color scales, and it was really a bad color scale. So I think that the community, and you also, as you mentioned, and you have worked on this visualization in your work from the ground-based LiDARs, it would be very interesting if you share some thoughts in the EarthCARE Calval forum specifically about this, and maybe you have some suggestions, because then we can forward it to the developers that they have assigned this, and we can ask them to include these color scales, and then maybe we can even start the discussion and decide in the community what is the best color scale to include for the operational products, because this pipeline hasn't been defined yet. So the website that they will release, the quick looks for during the real operation of the mission, when it will be available to everyone, this hasn't been decided. So now it is the time that this discussion can be done and be in order to decide.
Well, the way it works in practicality, there is already, let's say, preliminary quick looks that are only available to the people in commissioning teams. Some of them are okay, and some of them look like they're from the God.
From the gut.
It looks like they're a direct insult to God himself. Because they're noisy, and like you have said, they have been produced by people that haven't really worked with the data before.
Yeah.
It's an ongoing discussion, and I'm cautiously optimistic the level 1 quick looks, when they're released, will be okay-ish, but it's always it's a struggle, because you rarely get access to the person that's doing the coding itself. It goes through a couple of layers of ESA, and then the feedback is a bit slow.
And
you have to explain, why it's important to plot things on a log. But then the iteration comes back and it looks terrible, and you wonder what happened, and then you find out, they took the logs of things first, threw away all the negative values, and then did the smoothing or something, and then, because it's not only the color scales, it's how much you smooth the data, and even which floppy library
you're using.
I've personally had to found out more about how image show and p-color works in Python than I ever really wanted to know.
Yes,
but especially some of the Python tools that you think aren't doing any interpolation and smoothing really are, and you have to take additional steps to make sure they don't do that.
Yes,
and that's the confusion for many.
And even going one step further, if you go very much into fine tuning, even if we want to have a comparable, same color scale as Calypso, so that we can see one to another, and the people who are used for 15-20 years to watching Calypso cartoons to see something similar for EarthCARE, because of the wavelength issue, you need a little shift in the boundary. So even up to this point, we have to have everything thought, even up to this small point. Okay, so let's open this discussion, Nikos. Let's open this discussion in the chat, in the forum. Ask the forum.
Yeah, that's okay. Yeah, sure. It's a good.
If you want. Thank you for your question.
No, thank you for having me.
Thanks. Are we good to go with the next presentation? Can you handle it? 5 minutes, 10 minutes, 10 minutes, 10 minutes break.
So we're going back in plus 20.
12:20.